So I can tell you 4 reasons why the power-hydrogen pump RASER is a powerful quantum sensor. The first is the high signal-to-noise, especially SABRE and FIB RASER. It's incredibly high signal noise. And together with T2 infinity, this increased the sensitivity of fundamental RASER devices a lot into a microhertz resolution, which was shown in Nature Physics recently. Secondly, presumably the RASER will work with most of spin 1/2. The protons is the most difficult, and 15 and other carbon-13 and other rare spins should be easier. It has not been shown, but it should be like that. Third, the RASER operates at a very broad range of magnetic fields, and we have shown a few examples. So the first one was FIB, a FIB RASER at high field 14 Tesla from RWTH, a nice paper. Then from Baptiste Yolande, FIB RASER at 1.4 Tesla in angewandte Chemie. Then SABRE from TomTom, we saw a minute ago, a 1 Tesla RASER operating then in our group, my group, we showed the millitesla, the first RASER at all, in the millitesla regime. So you see, this is basically the whole field range where the RASER can be applied. There is no limit to the field. Why should it be? The Earth field and the ZUF laser has not been reported. It also should be possible. Okay. And the fourth, it is a simple device in RASER physics to test. So I proceed. So now we come to the derivation of the RASER equations. We are very general. We are not restricted to any laser. So we have a very simple approach. We have a kind of resonator, say a X resonator. X can be R, R, L, and E. So here we take a LC resonator, very simple. There's photons inside. So the photon field is oscillates in the lab frame, say with the frequency omega x, for example, 100 kilohertz, for example. The X resonator has a damping rate. So the damping rate is simply the frequency of this oscillator here, divided by Q, and Q is the quality factor. Basically, the lifetime of the photons in this resonator is defined by the Q. In a frame rotating with omega, the equation of motion for the photon field, B is a complex value, is simply first derivative is minus the decay rate times. So it could not be much simpler than that. So it's the first equation. I think this is simple. Next one. Now we take a spin system. Say we take a spin 1/2 spin system with a Lambda frequency with gamma s times B0. And we take a relaxation rate transfer. We call it gamma x. It could be a laser, maser, or RASER. Very general. And we have a T1 relaxation. Transferred and longitudinal. Now we assume the spins are pumped with a rate gamma x. That could be anything from DNP, SABRE, FIB, or spin exchange optical pumping towards the equilibrium population inversion. And the equilibrium population inversion, it is pumped towards the D0, which is the maximum possible equilibrium population inversion by the pumping. The D and the alpha, these are the 2 components here. This is the population inversion, and 2 minus N1, and alpha is the transverse spin component. And this green object, pumped by gamma x, is a very simple motion equation of motion. Alpha dot is decay plus oscillation. Is a kind of Bloch equation, if you like, in a complex space. And the population inversion is driven by the pumping towards the D0 and decays with T1. The omega 0 is the offset frequency, NMR offset frequency of the RASER. Now we combine these 2 systems. So now we combine and say, now the spin system is coupled to this resonator. So the photon fields and spins are coupled via the coupling constant, and the Gx coupling constant again is general. We can say for the laser, the coupling constant is simply the square root of the laser frequency divided by the volume of the laser times the matrix element, basically from ground state to excited state. And for the RASER, it's even more simple because we calculate that in general for spin 1/2. The coupling constant between the photon and the resonator is gamma times omega of the RASER divided by the volume, square root. So we arrive to the full RASER equation. So the differential equation for the photon field coupled to the alpha, to the transverse spin by this coupling constant. Blue coupling, green spin, red photon. Okay, and then now the transverse spins, it's basically the Hamiltonian, the free Hamiltonian here. And this is coupled to the RASER field, to the photon field, and to the population inversion. And the third one is the complicated one. The population inversion is driven by the pumping lost by T1 and feeded in a complicated way by this. And this makes the RASER complicated. Okay, it's only a single mode ray, but we are not at the RASER yet. We have a three-dimensional space, 1 to 3 complex dimension, basically, 2 complex and 1 real, D. We have a 3D space, and we can reduce it to a 2 space by applying the slaving principle. And if we do that, we get the RASER. So what is the slaving principle? It's a very general principle in physics, which says we can adiabide eliminate the fast varying variables. Aachen in 1978 has basically shown that for the first time. He showed this in a nice book. And it means that the slowest changing mode enslaves the fast changing mode F. Slow mode S enslaves, which means the fast mode F, the slave, follows adiabatically the slow mode S, the master. The slow one is the master and the fastest follow. And mathematically, you can show this, not too simple to show, but mathematically, this is identical to say the first derivative of the fast is 0. And now we can picturize this to the laser and the RASER. So who is the master and who is the slave? In the laser, the master is the slow changing photon mode. The rate is the optical resonator rate, and the gamma, the pumping of the laser, and the gamma, these are the fast changing atomic degrees of freedom. So the photons enslave basically the atomic degrees of freedom. Now the RASER is basically the opposite of this scenario. So Ironman changed its role, and Thor changed its role, and now Thor is the master, the RASER. The master is the low changing spin ion mode. So we have the relaxation. The spin modes are now directing the photons. The photons have to follow basically what the slow spin motions are doing. So this is a nice picture about the RASER. Now let's apply this to the SABRE pump RASER. We know the parameters. 1 SABRE pump RASER with Q to 100, say 100 kilohertz. So what is the resonance damping rate? Well, it's simply omega 0. It's 6 times 10 to the 3 seconds, or 6 kilohertz. What is transverse? Protons say 1 second, 1 second, 1 second to -1. And the pumping rate is from SABRE is known from 0.05 typically to 0.2. The realization rate, and now we can apply the slaving principle. It means that the damping rate is much larger than the other 2 rates here, the relaxation rate and the pumping rate. So we can enslave now this general equation, say the photon modes in equation 1, the photon modes B, the photon mode has to follow adiabatically the transverse magnetization, and coupled by these constants here. And okay, that it is. If we do that, we get what we call the RASER equations. It's a 2-dimensional space between population inversion and alpha. The photons are away here, so this can be transformed in a well-known form, which are called modified Bloch equations. So you recognize the Bloch equations here, mz dot and transverse. This is basically analogous to that with a constant here, gamma, h bar divided by tau times volume. So plus the nonlinear term here. Okay. Now, what is the RASER threshold? And there are many ways of defining the RASER threshold. I will show you the most simple. The threshold of the RASER can be derived from this equation, simply the losses of the resonator times the losses of the spin, transversal, divided by the coupling constant. That's a very simple expression. This has an analogous in the MESA community. The tau r to -1 is basically 1 over T2 star is equal to the transverse relaxation rate. That is, and tau r is the radiation damping rate. This is also well known, but now we have the connection to the synergetic motor. And in the resonance, in the magnetic hyperpolarized community, the threshold is simply the polarization you need for threshold is simply -4 divided by the constants here, divided by T2 star times number, density of spins times Q. Q is very important. The higher the Q, the lower the threshold, the higher the density, the lower the threshold. This product is very important. Of course, T2 too. Okay, now we can further reduce the two-dimensional space, transverse spin and population version, to one complex dimension. This is what happens, especially if the second adiabatic elimination process is valid. So if both are valid at the same time, so the resonator damping is much larger than the pumping, and the pumping is much larger than the transverse. If that holds, it does not hold in general, then you get a very simple equation for the transverse mode alone, split mode. So it's simply this factor times alpha minus L times to the power 3. It's a typical laser equation, which you find in many books, but now adapted to the RASER. And the threshold is simply, the threshold is when this is larger than 0. So if R is larger than the transverse relaxation losses, then the RASER exponentially rise up until this is taking it back. And the R can be generally formulated by this way. Okay, so now this is enough theory. Now I show you the single mode RASER equation simulated. I'll show you. Now it's pumping from the left, so the population version is MZ. Here's the threshold. At this point, now the laser starts to oscillate here, and then again it pumps again. You see it damped out here, and then again it starts to pump again to negative values. Then again it pumps. So the Z magnetization looks up and down. So this is a simulation from Mathematica. And finally, if you wait long enough, you get a continuous, say, motion of the spin vector here in three-dimensional way. This is the infinity 2 of the RASER with the Lambda frequency processing on the cone here. So the magnetization, the procession on the cone proceeds forever here. Okay, so this is a simulation. Now we want to realize this at low magnetic fields, say at 1 to 25 millitesla typically. And so we need a sustained population inversion. And Patrick has shown one way with a membrane reactor. I'll show you another way, directly bubbling in. So we say T2 starts 1 second, and we have, say, about 10 to the 20 spin, and the Q is at low field typically 100. So we need at least -3 negative polarization population inversion times 10 to -5. This corresponds to an inverted Boltzmann polarization for about 10 Tesla at 300 K. So this is what we need. And everyone in the conference knows that the SABRE approach easily can supersede this. Basically, from 10 to -4 to 10 to -1 for protons, this is standard SABRE. So we are far away from the RASER threshold for standard spin samples. If in addition in low field you have a higher Q than 100, then the RASER process is something very easy to do, and I will show you in a few minutes. So with high Q values at low field, you can do really every RASER experiment. So higher Q factors facilitate RASER activity of many molecules. If Q is 1,000,000, so probably every molecule will raise. Okay, we know that SABRE can create complicated, not only single spin order, so 2 spin orders. So we can study the RASER of, say, complicated spin orders. Stop. Okay, so now this is how it looks like. This was the first experiment for RASER. So we bubble in continuously at a few millitesla bubbles with a small syringe, a small pipe here. And so back, continuous flow back inside a resonator with several hundred Qs at, say, 100 kilohertz. That was shown by Martin in a Nature Physics 2015. And 2017, we showed the first RASER worldwide at all with this simple setup using pyridine or acetonitrile in an IMS catalysator process. So, and I don't need to talk too much about this because I had a lot of nice talk. Just to show you how that works. So here is the IMS solution with pyridine. This is Søren. Yeah, Søren was working in my group, so he puts into the RASER resonator and the EHIC resonator. We call this Thor's hammer because it looks like a hammer. Inside the field, it's about 166 kilohertz, and you see in single, that's the first RASER signal worldwide. We got that in Aachen lab. You can see the initial relaxation oscillations, so in practice in live, in vivo, and here in the oscilloscope, you can see the 166 kilohertz basically time resolved here. real time. So you can follow it after a minute or so, you have a continuous forever RASER signal. Okay, so and we have been surprising that this is so simple, but it is simple. Okay, now let's do a more complicated case now. And so I will not do the physics of that. The time is not sufficient for that. So, but I will show you something. For example, we have two modes. And two modes are starting to get complicated. So we get frequency comps in line collapse phenomena. What does it mean? Let's say we have a molecule which has exactly two NMR modes. Here two, they are separated by 2 Hertz. Delta mu1 is 2 Hertz. We assume that, so the RASER signal would look like that. That's a simulation, okay? Now what we do is we shrink the frequency, the distance between these two modes more and more and more and more. You see a lot of interesting effects. Number one, the shift, there's a small shift, it's called nonlinear frequency shift in the frequency, and it's larger the closer the lines are. So you can see delta mu1 here, and the green ones are far away, so it pushes away. And the second effect which arises are called frequency comp. So the lines start to duplicate. You see the small lines, it's exactly the frequency they will duplicate. This is basically frequency comp. It's analogous to the physicists who use the frequency comp for laser, precise laser, Theodor Hensch, basically. And now there's another interesting thing. It's called period doubling. So this frequency difference starts to get halved. So the period of the RASER has doubled. And so this is another interesting effect I will not talk about. It's just to show you how interesting that is. Even there are only 2 modes. And the period doubling now changes the shape. Suddenly the even number of lines here changes into an uneven, into an odd frequency comp to a central line and another spacing. So the next transformation, if you like, and if you are at very, very low difference frequency, 0.14 Hertz, exactly there is a line collapse. So the whole structure collapsed into one line. And we found out the condition for that collapse, it's to nonlinear mathematics, a well-known, famous phenomenon called mode locking or mode collapse. It's when this R, this constant R, which I showed you before, the renormalization, is larger than pi times the frequency difference. Okay, so can we observe the frequency comps in line collapse at low field at the millitesla? Okay, say the first attempt we tried, so it was CERN's idea, say we take picoline. Picoline at low field at 1 millitesla is incredibly complicated. One should not think that because, so I have always trouble here with this meeting, because the CH3 group is strongly coupled to all others and the frequency difference, ppm between CH3 and the ring proton is only a part of a hertz, 0.something hertz is the frequency difference. So chemical shift 0.24 and the J couplings are all in the same range. It's the worst thing you can do. Okay, so you have 4 + 3, 7 protons strongly coupled all between in Archer. So if you calculate the spectrum of this picoline at a millitesla or so, you get something like that. So these are hundreds of lines. So with a millihertz resolution of 10 millihertz, so this is a simulation, okay? At 41 kilohertz, we have some hundreds of lines. This is picoline at 41 kilohertz, okay? And now we introduce this effect that the R is larger than the spacing of that frequency. What happens? The RASER shrinks to one line, so it renormalizes, or it shrinks to once, and the RASER just pushes away all these fine splittings. If you increase the frequency splitting, you increase the magnetic field, you have a gap here. This gap is 0.15 Hertz, calculated by a computer simulation. Then suddenly you have the reverse transformation. The one single line gets into, say, an uneven frequency comp, an odd frequency comp. And then if you increase it much more, so say to 1.717 Hertz, so the average between these two groups, what happens, the RASER renormalizes this to one line and renormalizes this group to another line and builds up, say, another frequency comp with another spacing. So you see here in real time, it's strange, we call it giant pulses. And so at even higher frequencies, you get this, and so on and so on. And so it tells you that the RASER the nonlinearity of the RASER makes it very interesting to analyze basically ultra high resolution NMRs. Now here's experimental proof for the collapse. The prediction was at 41 kilohertz, even you have hundreds of finely splitted lines in the millihertz regime, you can only observe one RASER line, and this is here the case for free picoline at 41 kilohertz. So at 1 millitesla about, we did a lot of effort. We could never see anything else than one line, blue, green, and blue. At this 3 times, we made a Fourier transform and we analyzed all that. It's only one line, so it's dry. Here you have a line collapse, definitely. Even the system is quite complicated. Okay, but now if you increase the frequency, what happens exactly what we expected? We expected that a frequency comb happens. These are the first frequency combs observed, so whatever for a pH2 RASER pumped, to my knowledge. So this is a frequency comb, and it corresponds exactly to the theory. So the spacings here are really, say, they are really calculated and reflected in even the form here. The form here, the small line here of the even frequency comb or the odd frequency comb, the smaller line you can see here in the theory. See here, this is small. It's not the amplitude, but nearly. So so you have a small line in the middle, and then the uneven. So you can see this is not science fiction. This is real. This is real world, all happening at low fields. And the RASER is basically mistreating the molecules, if you like that. Okay. Okay, so now let me come to the last topic, and I promised you that even the single mode RASER, which is well known for many scientists for many years, even this has interesting features. So we can say that the equation of motion is simply reduced to d dot, the pumping term, the relaxation, and we say that the alpha, so the transverse motion, is basically a complex value, an amplitude times a phase factor. So this comes into the amplitude square. And the phase is simply, because it's a single mode, phi dot is simply one Larmor frequency of resonance frequency. Interesting, what we have here as a new element is the pumping rate here is not anymore constant. It's a function of time. So if the pumping becomes a function of time, then the things become interesting. It's not anymore relaxation or oscillation. So this is what we need to investigate this in detail, is a really pure single mode RASER. And a pure single mode RASER is pyracine, because the free pyracine, the majority, so all the protons are equivalent. There's only one mode. The bounded species not raising, so only the pure pyracine is a pure single mode RASER. Okay, so Simon and Sören were in Aachen, and we tried that without big expectation. But what is interesting is we can now measure the dynamics, what you have seen already with Patrick and what I showed you before. It looks like completely ordinary. So you start the power hydrogen supply, and you have the RASER action going on. It looks completely, but the mathematics of that is not simple. This relaxation cannot be explained by a steady state pumping. Cannot be, and you will see why. So what we did then, after the RASER is in a constant state, in the steady state, we applied a magnetic field gradient. So the RASER oscillations are killed, okay? And then the RASER goes into the maximum polarization possible, pumps up again from this state into the maximum state, stop the magnetic field gradient. Suddenly, you see it looks completely different from here. The initial relaxation is very fine spike, and then nothing happens. And so finally it turns into the same stationary state we had before. These are fluctuations. So this is not to do the pumping. I think these are fluctuations from the bubbles which are inside the liquid. But now comes the fun part. If we apply a magnetic field gradient, and you got this maximum polarization, SABRE polarization, and you stop the flow completely. After half a second with no flow, we have seen it by eye, no flow. You have, like here, an RASER, and now look what happens. No power hydrogen supply anymore. For 1 minute, you see this, you could say RASER revivals, a revival, another revival, and the revivals decay, like with T1. some kind of T1, and the width, if you look at the width of this revivals, becomes larger and larger. So in the initial state, we did not understand that, because standard theory says there's only one peak. If you switch off the power hydrogen, there's only one peak, and that's it. We did not expect here 5 other revivals to happen. So
we are now in the question and answer period. If you could please finish.
Yeah, I'm finished. So we could analyze that and found this is with theory consistent. Okay, and this the last slide before this one. So the possible applications are everywhere: medical science, fundamental physics, synergetics, chemical science, computer science, definitely electronic and sensors. We can use the RASER as a magnetic field sensor, the RASER as a low noise preamp, and the RASER as a gyroscope. This is definitely our applications. Computer science may be quantum computers because decoherence, no problem. Chemical science, catalytic process may be very precise measurement. Medical science, imaging. This is a new topic which I'm interested in a lot. In fundamental physics, maybe Dima Budka can talk about this dark matter research. We can use the RASER for search of dark matter, or cosmology, spin networks, fundamental physics here with spin networks, and synergetics, the self-organization. We have a new paper dealing with that. I come to the end. The summary is here. I showed the RASER equations, how to derive them. I showed the first demonstration of the RASER with pyridine. I showed line collapse and frequency combs are appearing. And finally, RASER revivals after switching off the power hydrogen supply. I thank you very much for your attention.
Thank you so much, Stephan. That was truly beautiful. And because we're out of time for questions, I definitely refer everybody to the Slack channel to answer questions. But just because there was one question here, I'm going to ask this one.
Okay, okay.
So if you do a RASER in the SOLV environment, what will be the acronym? Will it be for acoustic RASER? So maybe it would be ASER?
Yes, A quadrat, say maybe SABRE. Okay, from SOLV. Yeah, I don't know. You invented.
Okay, perfect. Okay, thank you so much for this wonderful contribution.
Yeah.